this gives you, first of all, the basic idea of sensitivity and the command-based scoring and the new scorer kind of things. So, as a very basic of the scoring or sensitivity, as I said before, I have already shown this slide before in my first talk, that besides of specifying geometry, picking physics, using physics what you need, and primary track to specify how you start the event, you have to do one more thing to say what data you need, what data you want to extract from Geant4. Okay? Without doing this, Geant4 will run it nicely. Maybe you got nice event display, but no number, no data. That's not nice. Okay? So there are basically three ways. The first one and the simplest one is the built-in scoring commands. This is enough and sufficient for those who need just those flux, energy depositions, like this kind of physics quantities. You can measure all of these kind of things by just typing some UI commands. You are done. Okay? The second option is associating this kind of scorer to a particular volume that you are going to specify. For example, even for the medical cases, if you want to measure the dose on the liver, for example, you want to say this is a liver geometry, so you have to attach your detector or measure associated with my liver. Otherwise, if it's just a box cells, you can simply measure the dose for each box cell. That's easy. That is the first option. But you want to say the dose on my entire liver, you have to say which part is my liver. Okay? That is the second part. And for those who are quite unfortunate to really need to simulate detectors, that means you need to have some output, like a signal or hit patterns or so-called Monte Carlo truth. You have to do this sensitivity detector thing. Okay? And completely another way is a la good old days Geant3 stuff. You have all the user hooks of user tracking action, user stepping action. So you can implement everything you need by yourself. And it's all information accessible. You can get everything. Straightforward, but do it yourself. And it's much more complicated if you run this in multi-threaded mode. You have to take care of all the merging after the thread. It's not that easy. While if you do this, Geant4 will take care of merging over the threads. So this is much simpler. So command-based scoring. This is the first, sorry, I cover only this part in this talk, okay? Because it has to be enough for half of you at least. So command-based scoring functionality offers the built-in scoring mesh and various scorers. Scorers means each scorer score whatever the physics quantity you want, like a dose or a flux or energy deposition kind of things. Okay? But because of the small performance overhead, this functionality does not come by default. You have to say you want it. The key is that in your main, Geant4 is a toolkit, first of all. You have to write your own main program. Okay? That we do in our hands-on starting from tomorrow. Okay? So in your main, you have to say RAM manager. If you use empty RAM manager rather than ordinary RAM manager, you run Geant4 in multi-threaded mode. Okay? Anyway, just after instantiating RAM manager, you have to access to the scoring manager. This will trigger all the instantiation, all the setup of all the scorers, just one line. Of course, you have to have header file included. Otherwise, compiler will not compile your code. That's it. Once you have this line executed, all of the UI commands necessary for this scoring functionality will appear in the score directory. Okay? And So I invite you to look at examples extended round event RE03 as the best example to demonstrate how to use the scorers. Okay. So this is that example, RE03, this one. Okay. This has the simplest ever geometry in our examples, even simpler than our basic example 1, because it has only one box that represents the world and one box inside that is filled by water, period. Big box and smaller box. And we shoot muons, actually, in this case. With high energy muon, that spits out a lot of delta rays. Okay? That's it. So nothing fun as is, but once you start to use scorers, you can really score all in this case, energy deposition in 3D or slices to see really the evolution of the shower or even the cylinder. So you don't have to write any single line of code, except, of course, the geometry itself. That is something you must. But for scoring purposes, just some few lines of UI commands. That's it. And for many use cases in medicine or space, this is enough. Okay? So to do this, of course, first thing you have to do is don't forget to have this line in your main. Then in UI commands, first thing you have to do is you have to define the shape and the name of the mesh. We currently offer box and cylinder shape. So you have to choose one out of these. Then you have to define the size of the scoring mesh. It's a bit louder. Okay, now it's better. Yes, thank you. Oops, sorry. So you have to specify the size of the mesh. Please note the size has to be specified as half width. I'll come back to this when I discuss about geometry. But this is an example. The first lines correspond here. Score create box mesh. That means we are going to create box-shaped mesh with this name. Okay. Name always has to be unique. Then size. This is actually 2 meter, 2 meter, 2 meter. 2 meter wide, 2 meter depth, and 2 meter high. Okay? Because they are half widths. Okay? Then you have to specify number of beans for each axis. In this case, I said 30 beans, 30 beans, 30 beans. Okay? But be careful for this. Don't employ too many beans. It's just simply eat up memory. You can simply calculate. If you have 100 times 100 times 100, already million, right? Million byte, at least. Okay? So be conservative here. And if you want, you can specify the position rotation of the mesh. By default, it is set at the middle of the world volume without any rotation. But you can say put it here or there with rotation. Okay? And the mesh geometry, mesh can be completely independent to real-world geometry. So you can put it anywhere without even worrying about if it overlaps with something. So just press the mesh. It's a conceptual mesh. Okay? So we have a lot of different scorers. Each scorer scores just one physics quantity. In this case, energy deposit per cell, this cell charge per cell, flux, and so on and so forth. A lot of different. For example, number of trucks or number of secondaries generated, number of steps made in that volume, and so on, or in that cell, actually, and flux. There are a few definitions of how flux or current are measured. Okay. So just use specify, and actually you can measure more than one physics quantities. Those flux, what energy deposit, number of steps or whatever into the cell. And also, you can apply filters to each individual scorer. Please note, it's a bit complicated. Charged filter means it does not filter charged particle, it vice versa. It accepts charged particle. Okay? If you apply charged particle, you score the physics quantities only for the charged particle. Okay? Neutral particle filter scores only the neutral. And kinetic energy filter, that score filter kinetic energy with name, low and high limit and unit. Okay? So if you want to measure the flux of, let's say, neutron, only for this energy region, you can use this. Okay? So it has to be higher than 1 MeV, let's say, and lower than 1 GeV. You say that. Okay? And this is particle type filter. You can list whatever the particle names you want to score. Okay? And this one is a combination of this one and that one. So it takes name, low and high energy limit with the unit, and particle names. Okay? So here's an example. I forgot to say, I believe, that this is the first part. You define the mesh. Once you define the mesh, then you start to define scorers with such a command. Score quantity, this XXX means any name. And with a unique scorer name, and unit if you like. Otherwise, Geant4 will score with Geant4 internal unit. But even if it's the case, you can always divide by unit to get the number as you like. But also, it's better if you specify here. Then if you visualize the score, unit will be written. Okay? Of course, unit is needed only for the real physics numbers. Number of steps, for example, you don't care. Okay? It's integer. Okay, then here, the filter. So I start to say, I'm going to score energy deposition. This is the scorer name, and I'd like to score it in the unit of MeV. So one thing done. Then I say, I also want to score number of steps with this name. You don't need unit because it's integer. But say, I want to associate this filter with this scorer. That means this is gamma filter, so particle filter, right? So this particular scorer will score only for gamma. That's the reason why I put the name here, number of step gamma. Okay. Now you employ yet another, but exactly same kind of scorer with different name, with different filter of electron, so that you can measure number of electron steps, and so on and so forth. Okay? With such, you can define whatever the necessary number of scorers with filters. Okay? And once you're done, please don't forget this one, score close. Then you say all the definitions are done, and you are ready to start the event. Okay? After the run, you want to visualize it, of course. So draw projection is something it's a 3D projected picture. In this case, you say the mesh name. Mesh name was defined. Oops, where was that? Here, yes. That is the mesh name. Then scorer name. So if you want to visualize, for example, energy deposition, you have to say EDEP here. Okay? Then if you want, you may specify the color map. By default, we have both linear and long scale color maps. But if you want, you can define your own. Okay? And minimum and the maximum values are taken by default by the minimum and the maximum of the beams. But you may also want to specify the min and max. Okay? And for the case of slice, basically argument is the same, but you have to say in which axis you want to slice, you want to make a slice, X, Y, or Z, and which column number you want to slice. Okay? So actually, in this case, I visualize 5 slices. Okay? And this is, again, this RE03 example. So if you are interested in this afternoon, you may try this out. Okay? And of course, drawing is important to convince your supervisor. But you also need values. Okay? So here, write scores to a file. This is even more important, So score, dump quantity to file, mesh name, scorer name, and file name. Okay? If you want everything into one file, here, score, dump all quantities to file, mesh name, and file name. That's it. And by default, values are written in CSV, comma-separated values. That is readable by basically all the analysis tools, including Root, but also Excel, if you like. And also, if you want to have it in your experiment-specific format, you can override score writer to write your format. Okay, write in your format. And starting from this 10.5, we also directly support root file. So if you want, instead of CSV, you can say write in root format. If you are confident to use root, I don't necessarily recommend. Okay. And one of the most frequently asked questions, in particular from our space users, they want to get energy spectrum. Do you have any particular scorers? No. But create arbitrary number of flux scorers of same kind combined with particle and kinetic energy filters. Okay? So here's flux number 0. That scores (10 to 20 MeV electron. Then next one is 20 to 30 MeV, and so on and so forth. You got spectrum, right? And also, don't be afraid of 100 lines here, because we have loop command. It's easy. Okay? So instead of creating all the different options, we offer just the basic ones. But with a loop command, you can do whatever you want quite easily. Okay? So if you go to the Hypernews and check how many questions of this appears again and again, yes, but just take this recipe, you are done. And also, you may define more than one scoring mesh. In this case, I created 3 different meshes of different size at different locations. And you may define arbitrary number of primitive scorers to each scoring mesh. Okay. And mesh volumes may overlap to each other, if you like. Okay. And also with mass geometry. So you don't need to worry about overlapping with other volume at all. Okay. Please note that a step is limited not only by the real volume boundary, but also the mesh boundary, because we have to score the dose per box cell, per cell, so that we really need to limit the step by this cell boundary, so that we really know how much of energy comes into this cell. That means if you have much granular meshes, you will see much more steps. That causes a bit of performance overhead. And individual event may change because steps are limited, so we consume more random numbers. But statistically, it should be the same. Okay? But event by event, it will be different. And please be cautious to too many meshes, because it eats up memory. Okay? So once you realize Geant4 is unnecessarily slow, just check how often it accesses to the disk. Okay? If memory is too huge, portion of the memory is written in a disk and read back and write back and so on and so forth. That can easily destroy the performance for 2-3 order of magnitude, quite easily. Okay? So just check the size of your application. Okay. Any question up to now? Yeah, you will try it out. Yes.
When you showed in the slide when you were defining different scorers.
Yes.
And you had the energy deposition. What is that?
Yeah, this is.
Filter, right?
Yeah, the filter is applied only to the exactly previous command. So this filter doesn't apply to this one.
Yeah.
So if you want to score the energy deposition for particular kind, you have to have filter here.
Yeah, I understand. But let's say I was interested in an electromagnetic shower. So I have a primary gamma that will make an electromagnetic shower. Further gammas and electron positons, etc. If I don't do any filtering, it will get everything.
Yes.
But if I dare to do something like that and I want all the energy deposited, then I will have to make a filter for each one.
Yes, definitely. Once it is mixed up, it's too late.
Yes.
Okay. So now I continue to add a new scorer filter. Okay. You now need to write a code, C++, because you are now adding a new functionality for Geant4. And all the details of this method is something we are going to discuss in my second talk of scoring for detectors. But basically what you need to do is you have to fill basically the 4 methods in addition to the constructor. The first method of initialize, you have to initialize the map that your scores are going in. Then process hit, this is the most important method you have to implement. Here you get the hit, you get a step. So from step information, and also you can have access to the track information. So you have all the information you need. So you have to extract whatever the physics quantity you need. Okay? Energy deposition is simple, but some complicated physics quantity you have to calculate and score it and fill it in the map. This is something you have to implement. And clear is obvious. And get index is something I'm going to discuss in my geometry talk, but how you index the cell. Because it's a map. So map, it means one integer index is mapped with value. If you have 3-dimensional cells, there are 3 indices, x, y, z, or ix, iy, iz, I should say. But you have to calculate by some way to get one single integer number. That should be the key. So you have to implement what is your ordering index. Okay? So I suggest to look at this code, go to the LXR code browser, type this class name. And as you see, it's energy deposition. That is easy to understand, the concept, and also easy to implement. So I suggest you to start with this code and copy it, change the name, and add whatever the physics for this method. Okay? And once you are done, you have to have your own UI command that I'm going to discuss in my user interface 2 talk to define your command and define the command. Okay? Here's an example. Sorry for this stupidly long class name. G4 scorer quantity messenger Q command. I don't know what this Q means. Anyway, this is a class. Just you look into the implementation, how to define a particular scorer command. So here's a methods. Okay, they already appear here. And equal 0 means it's pure abstract, so that you are not allowed to instantiate any object of this class. I'm sorry. Oops, where am I? Without implementing this particular method. Okay? So methods written in red will be discussed again in the scoring 2 talk in more detail. Now filter is the same. In this case, you have only one abstract method, partial method to implement, accept. So you get the step. From step, you can reach to the track. From track, you can go to the particle definition, for example. So do whatever check and say yes or no. Okay? If you say yes, that particular step will be scored. If you say no, it will be discarded. That's it. Question? So you will try at least the first part of my talk, the scorer part, tonight, not tonight, this afternoon, and also tomorrow hands-on, quite a bit. So you may just recall what I presented here today when you really try it out tomorrow, okay? Okay. Sorry.
So we will start the physics part with this lecture now. There will be 3 general physics part. This one about the physics list. Here you will see in the physics list I will mention processes, but I won't explain what a process is. That I will do in the second physics lecture tomorrow. But you will see even here today and tomorrow in the processes that I will talk about electromagnetic physics and hadronic physics and some others like decay, and you heard about special things like optical photons and so on and so on. So the third general will contain everything that is not electromagnetic and hadronic physics, and we will have 3 lectures on electromagnetic and 3 lectures on the hadronic physics. Okay, just in advance the structure a bit. So we will start today the physics with the physics list. And what we will talk about here is that, first of all, what is the physics list concept in Geant4 and why do we need it if we need at all? Then we will see that what are the user interfaces provided to build up a physics list, or you will see that there are some physics lists in Geant4 available given by the toolkit that you can use as it is, or you can take some part of those physics lists and put together your own. So let's start with the very beginning and try to see what is this physics list concept in Geant4. Now, the physics list in a nutshell is a collection of the particles that you want to use in your simulation and the physics interactions that you want to use for them in your simulation. Okay, if you have a simulation, you build up a nice geometry, and you even have you cannot have a particle gun already if you don't define any particles, because the primary generator needs to generate particles. No? So you need to define somehow a list of particles that you want to use in the simulation, and it will be the physics list, together with the list of processes, interactions that the individual particle can have during your simulation. And as Makoto mentioned, the physics list providing the physics is one of the three mandatory objects that you need to provide in each Geant4 application. The first one is the detector description. Then the second one is the physics list itself. And the third one is your primary generator action. If you think about these three, with the detector description, you described your geometrical setup. With the primary generator, you describe how primary particles arrive into your setup. And with the physics list, you describe how all the particles that will appear eventually after your primary particles will interact, the way of the interactions, possible interactions. You will see examples soon. You will see that this physics list, there are different levels of you getting a physics list for your application. You can done it with one single line, okay? Or you can build up everything by yourself, starting putting there particles like electron, gamma, whatever, then all the processes. So you will see that this physics list concepts and the interface provides a very general and very flexible way for the user to set up the physics environment. Pick up your particles that you want to use in your simulation and define your processes, and you are done. But at the same time, you need to be very careful, because if you forget an important interactions in your simulation, that your simulation will give wrong result. Okay, if you are simulating electromagnetic shower and hitting your detector with a high energy electron, and you forgot to add Bremsstrahlung photon emission, that your simulation will totally useless and gives bananas. Okay, because you forgot to add a very important interaction into your physics list. But I will mention this several times. So the next question is that why do we need this physics list? Because we know what are the particles, we know what are their possible interactions. So as any other simulation toolkit, we could give a default physics list, and you don't even know what are the particles and what are the interactions, and the simulation would be fine. The answer is yes and no, because Geant4 is a general physics simulation toolkit. General means that you can simulate very low energy electrons, for example, interactions, up to TV and PV interactions. And there is no application where you would need to have all this energy range and all the models that we are providing. Because in Geant4, it's not only we provide a process, for example, to describe Compton scattering, but we provide a 5 or 6 Compton scattering model based on different theoretical background. Okay, we describe the interactions based on different approximations. The stronger approximations we are making to describe the interaction itself theoretically, the simpler the model will be, and usually faster to compute what happens in the interaction, but we will lose some accuracy. It doesn't mean that we cannot compute it more accurately. We can describe more accurately, but it will give more accurate results, but we require much more computational time. No, for some applications, for example, you will see in the electromagnetic part we have different categories. We have some kind of categories called standard electromagnetic interactions and low energy electromagnetic interactions. It doesn't mean that there is the Compton scattering is described in the low energy and in the standard as well. Okay, it doesn't mean that we don't describe some interactions here or there. The meaning of these different categories is that in the standard we describe it in a rougher way, because the standard is used by high energy physics applications, because they do not care about shell structures of the atom and how it enters into Compton scattering, for example. But medical applications, they do care a lot about all the details, because they want to get a very accurate simulation result. So should we put together a physics list for high energy physics applications that will be optimal for them, but will be practically not really useful for medical physics applications? Because we should make a choice if we decide to provide only one physics list. But this is the reason that there is no one physics list. And there are as many as you want and even more because each of you can create your own physics list. Moreover, after tomorrow, you will see, after I show a few things regarding the processes, you can create your physics list mixing some Geant4 processes that are already there with the physics interaction that you write by yourself. And you can plug in and you can do the simulation. So this is why the physics list concept is a very useful thing. It gives you this very flexible way to set up your own physics for the simulation. And this is why Geant4 does not provide one physics list, but we provide everything. No, it's not true actually, because we are giving several physics lists, as you will see by the end of this lecture. So let's see. I mentioned already processes. I will keep mentioning processes without defining them. But roughly, when I'm saying processes, you can think of one particular type of interaction. You can think about Bremsstrahlung photon emission, okay? Or I've already mentioned Compton scattering of photons. This is one process, an interaction channel, if you want, for a given particle. So, what kind of groups we have regarding physics in Geant4? I already mentioned electromagnetic physics, and I mentioned that there are some subcategories inside the electromagnetic physics. One that we call standard electromagnetic physics. It's used by high-energy physics applications. So this contains models to describe the interactions that will be faster than in the low energy part. Still not bad, okay. But if you want a really accurate description even at low energies, because high energy physics interactions, high energy physics usually do not have too much interest in low energy electrons, low energy photons, okay. But if you want to do simulation with low energies, we have a set of physics already implemented, processes, models for low energy application. These are in the low energy category. I will talk about it on Wednesday. All these things. And Makoto already mentioned we have some special things like DNA. This is really interactions at the DNA level. You will see it's a completely different view of the story. Now, we have the decay physics, of course, that's the special things. And we have the hadronic physics that Dennis will talk about Thursday. And we have something that you can call parameterized or fast physics, fast simulation. It's just mentioned here for the completeness because we are providing an interface for this. So you can implement this kind of things and plug it in and do whatever you want. Okay, I don't talk about fast simulation here, but I just want to mention that there are interfaces available for fast simulation. Now, let's get back after this first view on the physics to the physics list. Now, we will start from the more complicated way to build up a physics list, and we will end up in a simpler way. I told you that if you want, you can get with one line, actually with a string, you can already get a physics list and you can run your simulation with that physics list. We will get there, but we will start at the deepest level. What is the core physics interface that's provided by Geant4 to build a physics list? It's called G4V user physics list. Okay, you see everything that is in the toolkit starts with G4, and if you see a double V after, then it means it's virtual. So you need to. It has some virtual methods that you, as a user, you can take. You derive your own class and you implement that method. Okay. So how we use it as an interface. This is what is an interface, just for those, I don't know how familiar you are with this. So let's have a closer look to this G4V user physics list interface. As you can see here in this code, this is the definition of a derived class already from this G4V user physics interface. So this is how we use an interface in C++, that we take the interface, we derive our own class, and we implement the interface methods. So when we give this object to the kernel after, it will call the interface method and will execute the code that we will implement in the interface methods. You can see the virtual methods here that we need to implement. So you can see that there is a method called construct particle and another construct processes and a set cut method. So there are 3 virtual methods. Let's see them one by one. So I told you that the physics list is the point where you define your particles and the processes. So the physics, the first interface method, the construct particle method, is exactly the place where you define your particles that you want to use in your simulation. You can see in this example that you can list the particles. You can construct an electron, gamma, proton, neutron, and so on. But if you don't want to do it one by one, Geant4 provides already grouping of the particles, like you can create all the bosons with one line, for example. It's a bit easier like this. So the construct particle is the method where you list create your particles that you want to use in the simulation. Now, the construct process, the second interface method, as I mentioned, the process is the object that will describe one way of interaction. Like, for example, one process is a Bremsstrahlung photon emission. Another process is Coulomb scattering. Okay. So the construct process will be the place where you define, you create your physics processes, and you assign them to a given particle. So Makoto mentioned that Geant4 will always track particles in such a way that we will stop at the boundaries. So the end point of a step is defined by either some physics interactions or some user limits, or some geometrical conditions. And it will be the transportation process that you need to add to each particles. Okay, no matter each particles, there is one process, the transportation, that need to be there, because this will be, if you want, you can think about transportation process as the geometry process. Okay, this transportation will talk to the geometry and we'll always know where is the next boundary there, and we'll handle these kind of things. So this comes in the physics list. You always need to add transportation. And beyond that, you can add your own helper methods that I did like this: construct electromagnetic and construct general. This is nothing I just created in my things. But let's have a closer look what I'm doing in these methods. This is the construct electromagnetic part. So don't forget, in the constructor process, eventually what should happen is that some processes need to be created and assigned to some particles. So how we do this? We first get this physics list helper that will help us to make the assignment. Okay. Then, after we, before this construct process method will be called, the construct particle method will be involved. So all the particles first are created. Then after we will get here. So we will go through the list of particles. In this loop, you can see we have an iterator for the particles. So each time when we go through, we get another particle here from our list. Okay. So how we create and assign processes that we check, for example, here, if the current particle in the current iteration is a gamma. If it's a gamma, then we can say, okay, what processes I want to add to gamma. I want to add the gamma conversion. Okay, I want to add photoelectric. I want to add Compton scattering. And with the physics list helper, it's very easy. You create the process itself, and you assign to the particle, which in this case it's a gamma. Okay. G4 gamma conversion, I don't talk about it at the moment, but you can think that there is already, by the Geant4 developers already wrote a process with the proper model to describe gamma conversion. So with this constructor, you call it and you have it. And there are hundreds of processes already available for many particles. Now, another case, if it's an electron, then you want to register Bremsstrahlung, ionization, Coulomb scattering, and so on and so on. Okay, so this is the way in which a physics list needs to be built up by yourself by hand. This is the electromagnetic part, and if you want to add, for example, a decay, where decay can be assigned to several hundred of particles, the same process, then you just choose to do it in a different way. First, you create the process itself, and the process has a good property that it knows whether it can be assigned to a particle or not. Okay. So in the iteration, when we go through all the particles in the table, we just check if the decay process can be applied to the current particle. If this is evaluated to be true, then we assign, as before. Okay. So the third interface method, I won't talk about it at all. I just mentioned this is setting production cut. I will talk about what production cut is tomorrow or after tomorrow. Then it will be clear. Okay, but it's there, this possibility. I don't want. I put it just for completeness. Okay. So what do you think about this physics list? So today afternoon you are ready to write your physics list. After this, I think no, and I can tell that most of the developers, Geant4 developers, has never written any physics list by themselves. So there are very few people actually who are manipulating physics list. Few of us are doing because we are doing the physics development. So of course this is not the only way to get physics, fortunately, because we would have significantly less users, I think. Geant4 provides another way that is significantly easier to use, to put together still your physics list, so you still customize a lot your physics list, but in a very, very easier, much easier way compared to the previous one. And this is the modular physics list concept. And the reason is exactly what I mentioned, because you could see this is fine. If you put all the details by yourself, you try. But it's very complicated and very long procedure to put it together. So the concept behind this modular physics list, and as I mentioned, that physics can be divided into some categories. So electromagnetic physics, hadronic physics, decay, hadron inelastic, elastic, and so on. So some bigger building blocks. And for example, I don't care about the hadronic physics, okay, neither decay. I care about the electromagnetic part. So I want to make my physics list, as I showed, in a detailed way in the electromagnetic part, because that's very special in my case. But the hadronic part, I just want to take it as it is and put it there. And this is what the modular physics list concept provides you. So you can take some so-called physics modules and put them together to build up your physics list. And as I mentioned, there are some modules in the electromagnetic, some even more modules in the hadronic physics or decay and so on. And how it looks, again, the interface, the Geant4 interface to do this by yourself is called G4V modular physics list, and you derive your own physics list from this base class. Then the first thing that you don't see the transportation here because it's automatically added, the transportation. And what I do here, you can use the register physics method of this base class to add such modules that I was calling modules, okay? And here I choose something like G4 EM standard physics, whatever is that. I will talk about it tomorrow and after. But you can see that this is something provided by the toolkit because it started by G4. And I add the second one, I call it your proton physics. So in this case, this G4 EM standard physics is one module called constructor, actually, given by the toolkit. So when you install Geant4, this gives you actually a set of particles that has electromagnetic interactions. You can imagine that electron, gamma, positron, and so on are everybody defined there, together with all the list of processes. So for electrons, Bremsstrahlung, ionization, Coulomb scattering is already added. For gamma conversion, Compton scattering, photoelectric is already added. So you don't need to care about that. So with this one line, all the electromagnetic physics is there. Okay. And you can take care of yourself regarding, for example, proton interaction in this case. And how you do this? These modules that I was referring to, modules, these are called constructors, physics constructors. They have a base class, and you derive your own constructor, in this case, your proton physics. And you can use the construct particle and construct process in this case as well, like in the general physics list interface. But here you will construct the proton, and here you will add the proton interactions to your proton only. You care about this part. Okay. So let me show a few things on the electromagnetic side, because we were using G4EM standard physics module. But this is not the only electromagnetic module that you can choose. Because this G4EM standard physics, I will talk about it, these kind of things, in the electromagnetic one lecture. But this is one set of models and particles and processes, and actually models to describe these processes, that's used by the high-energy physics applications. We have several options, because even the high-energy physics applications, ALICE, CMS, does not use the same electromagnetic settings than Atlas, for example. Then you can imagine how we could give one physics list. So we have different options, still used by other HEP experiments, with slightly different settings and so on. Or we have even low-energy constructors, like the Livermore and so on, Penelope and DNA physics. So you can see, you could choose all of this and change that one line that I showed here in your physics list to get a slightly different electromagnetic physics description in your physics list. So as you can see, you will always find the way if you want to get more information on these constructors, but I will talk about the electromagnetic part later. So this is a bit better to start and put a physics list together in this way, but not too many people are doing this, because it's still complicated. But unfortunately, it's like this. But this is still not the way that most of the user will go, because Geant4 provides already full physics list that you take and you plug in, and your simulation will contain 400 particles, more than 400 particles with a full set of interactions. They are called predefined or pre-packaged physics list. And the reason why it's done like this, that we are providing some full physics list, is there are more than one reason. First of all, as you could see, it's not easy even with the modular physics list to build up your physics list. It requires lots of knowledge to do this. The second is that there are physics lists put together by the developers for some specific applications. You can see some high-energy physics applications, but you can see some other medical physics-oriented applications, for example. And if you are coming from the medical field, for example, then you know where to start. Okay, you don't want to start from scratch to find out what processes you need to put into your physics list for protons, for example, or if you need to do anything with protons. You come from the same application area, you can start with something like this immediately. But we don't say that this will be good for you. we say that it's a good starting point. This is always the user responsibility to take a physics list, then start to change the physics list. Okay, add some extra interactions, extra particles or even processes to the physics list that's relevant from that particular application. Okay, or remove something that's totally unnecessary there. Okay. Now, these are this pre-packaged physics list that, as I mentioned, they are ready to use complete physics list. But again, we cannot say enough that you need to be careful because these are starting points into your simulation. So, as I mentioned, you need to take it. If you take it, you need to choose one. You will see a list soon. That's more or less matching your application area where that physics list is used, and you start to validate it for your application. Make sure that everything is fine regarding the physics description for your case. And you can see this physics list, as I mentioned, that they are complete physics list and used by big communities, I would say, like the Atlas or the CMS experiments. So they are used regularly. There are billions of events simulated with such physics list. So they are quite robust, and they do not change a lot in time because all the changes were done already. So I don't say that they are constant, changed very little, but they are regularly tested. So you can see many names here. If you have been using Geant4, you saw for something like FT, BERT, for example, and so on. If you were always wondering what this means, as I did before I knew, there is a naming convention for physics list in Geant4. Now we will see things like QGS, FTF that don't care at all. Dennis will talk about all these things actually here in the hadronic physics part. After the hadronic physics lecture, you will know what is the Quark-Gluon string model or the Fritjof model, or what are these intranuclear cascade models, and so on and so on. But you can see, if you see something like FTFP BERT, you can see immediately, okay, it must be something to do with the string model, then it must be something to do with that lower energies to the intranuclear cascade model, and you can have something like underscore HP or not, that will have something to do with whether you are using high precision models for neutrons or not, and so on. So after after this week, actually, if you see a physics list name, that you can read it. You will understand what physics is roughly put together in the physics list, in Geant4 physics list. Now, at the end, if you come back, there is no any, here you can see the only one where there is some EMV. And here EMY, but there is no any EM options. Now, at the very end, if there is no something started with EM, it means that actually it's the EM standard that is used in the high energy physics applications. Now, I told you that there are different options regarding how it's always, these options are always a trade between speed and accuracy. Okay, and option 0, which is the standard, it's a kind of compromise that won't be the most accurate, but not the fastest, but not the slowest. Okay, option 1 will be faster, but you need to be very careful to use it. Option 3, it will be slower but more accurate. And the most accurate, this option for physics list, this is the most accurate electromagnetic settings that we can do today. And you can see that there are some suffix for each of them that you will find at the end or not. If you find at the end EMZ, okay, at the end of the physics list, we'll end it with EMZ. You know that the electromagnetic part is described by the option 4, this very accurate physics constructor. So, just to give an example, FTFT BERT, first of all, there is nothing at the end regarding HP and nothing at the end regarding EM, so it does not use the accurate high precision neutron, low energy neutron package, and it will use the EM standard physics, okay, because there is nothing at the end. And you can see that FTF is for the Fritjof, Bertini is the Bertini internuclear cascade, and so on. Now, QGSP, big HP, possibly underscored EMZ, you can see what is the meaning of the different substrings. Okay. It's just to see what's the meaning of the substring. You will see what EMZ means actually, HP, big, FTF, QGS. Okay, you will see all these things during this week. So, let me show a few examples if we want to put together some physics list. For example, we want to put together this QGSP, big HP, EMZ physics list. Now, the point is that there is no physics list like this. You cannot get it with one line. But we have something like QGSP, big HP for the hadronic, you can see. And we have, as I showed you, we have this EMZ option in the electromagnetic. We have this module and that module. The only difference is that we need to change the electromagnetic part here because there is nothing at the end, so it has the standard. Okay, so we can create this physics list, this modular physics list, and in theory we can take the hadronic constructor that will contain the QGSP big HP part, and we add the EM standard option 4, that is the EMZ part. And with these two lines, you can end up with this physics list immediately. So this is the power of the modular physics list. You can see immediately you can combine two big chunks, and at the end you will have a much more accurate electromagnetic option here than the default EM0, actually, the default. But there is an even easier way to do exactly the same things. If you want to change, if you want to take a predefined physics list that comes with, for example, the standard electromagnetic option, and you want to change only the electromagnetic option, which can happen in case of medical application or whatever, that you want to check your simulation with the most accurate electromagnetic settings and stepping. Then Geant4 provides this possibility, which is very nice, through the G4 physics list factory to change the electromagnetic option in a predefined physics list. So you can see this physics list factory will know everything about the predefined physics list and everything about the available electromagnetic constructors. So whenever you pass a string like this, QGSP, big HP, EMZ, then what will happen? This string will be divided into parts, okay, and the end string will be analyzed, and internally, the physics list that corresponds to this string combination will be taken, its standard electromagnetic part will be thrown away, and the EMZ electromagnetic module, the constructor, will be put there and completed, and you will get back a pointer to this physics list. So with one string, you can even change a physics list. You can see. So, as you could see, physics list is the point where the physics environment is described. where you define your particles, the list of particles, and list of processes that you want to use in your simulation. And actually, you assign the processes to particles. And if you want to do your physics list by yourself, you can go and use the G4V user physics list interface, where you need to do everything by yourself, okay, defining the particle, all the processes, and assigning. Or you can go for this G4V modular physics list that you can use bigger building blocks to put together your own physics list. Or if you are satisfied with some physics list, complete physics list that are currently used by some application areas and are available in Geant4, you can pick them, one of them, easily with one line, and you can start to use in your simulation. But don't forget to make sure that that physics list is really good for your application. Okay, again, if something is not described with the appropriate model, because we do not count something in that model that is put into that physics list that you picked up, that's important in your case, then your result won't be good. Okay. So that's it regarding the physics list. Any questions? Yes? Yes. First of all, the best thing in the Geant4 things, as Makoto already mentioned, I mentioned, you will see tomorrow regarding the processes, that when I'm saying that Bremsstrahlung is implemented and available, I'm as a developer of the Bremsstrahlung process, I took the physics process interface of Geant4 and I implemented there something. You, as a user, has the same possibility. You can take the interface and you derive your own, you write your own Bremsstrahlung process. You need to implement 2 or 3 methods, okay? So you can put everything there. But we are using the most accurate the slowing down approximation, it's not really the physics, it will be more in the electromagnetic part. But this is how you describe practically ionization and Bremsstrahlung in the simulation. Whether you describe by a mean energy loss everything, and you have the full stopping power, actually the radiative part from the Bremsstrahlung and the ionization part together, and when you are talking about the slowing down approximation, this is what it means when you are thinking in stopping power and range. No, the other limiting case where you describe everything, you emit all your Bremsstrahlung photons, okay, even the lowest, if you want. You emit all the secondary electrons from ionization, even with the lowest energy. Then you describe everything in an even by even basis. For example, this is what's happening in the G4 DNA physics description. No, this is possible to do at low energies. Because you will see, I will talk about it, because the problem is that there are so many low energy photons emitted. It's just because of the characteristic of the differential cross sections for Bremsstrahlung. Or there are so many low energy electrons that in the ionization. It's again the characteristic of the differential cross section. That if the energy, primary energy, is higher than I don't know, few hundred kilo electron volt, then the simulation is just becoming really unfeasible. Okay. So what is used in the high energy physics simulation, even in intermediate energies, is that kind of condensed history simulation technique for ionization and Bremsstrahlung and even for Coulomb scattering, but this is another story. And I will talk about it in details tomorrow and after tomorrow, that we actually combine these two ways of description. But we have, I'm not aware of anything that we don't have the most accurate possibility to describe these things. But if you think, you can go and you can implement the process, plug it even into the physics list, and use your own. So this is one of the biggest power of Geant4. And it's true for the geometry, as Makoto mentioned, it's true for the physics. It's true for everything. Yes?
You made a clear point that you can choose, when choosing the physics list, you can play with this trade-off between accuracy and computational time. But of course, this depends on which physics you are running or the complexity of your model. But is there some kind of order of magnitude of this scale? I mean, if you go for computational time, you can go up to, you can be 2 times faster?
Yeah. Within the normal cases, because if you are not in the normal cases, but for example, you change one line in your physics list, and for electrons in your physics list, you put Coulomb scattering, and you don't put multiple scattering, then it means several hundred or thousand times in your speed. Okay, but this is pointing more into the discussion of how we describe Coulomb scattering in the high energy physics. I will talk about this. We describe, again, in a condensed history way. Just because it's not feasible to describe individual elastic scattering at high energies. It's impossible. So small mistakes like this can cause even 1,000 times slowdown. Or if we are within the normal electromagnetic option parts, but we will talk about it after tomorrow, then you can see factor of 3, 4, 5. Depending on your geometry, it can be even 5. Because with these options in the electromagnetic, we're not just giving you a better model to describe what I was mentioning, Compton scattering, for example, if you are going to EMZ. But the tracking is much more precise, which means, again, it's connected to the multiple scattering, the Coulomb scattering description, that we do not allow to make any errors. Now, what error means in the tracking, it's another story, but more precise. That will also depend on your geometry. Okay, you have a more granular geometry, this EMZ will be significantly slower. If you have bigger crystals, then it will be still, factor of 2 only, which is kind of only. But on Friday, at the end of this week, today I was already talking about this physics list and how to choose the physics list, few points, okay. First of all, there is no recipe. I cannot tell you that for whatever application, you take this and it will be fine. You change only that. No. Unfortunately, each application needs to choose the proper physics list. And this is the responsibility of the user to choose the proper physics list. There are some guidelines, and this is what we will try to see at the end of the week on Friday, in a way to see more things. Okay, some kind of collection of the week. Some other questions?
Is there a way that you could do, for example, probably you have to make something yourself, right? You said that to set up multiple scattering and high energy physics is physical.
Yes.
But maybe you want to track down this after the particle has decreased in energy, and then from, I don't know,
No. No, yes and no, because there are special models for that. So for Coulomb scattering, it goes a bit further, unfortunately, even than this week I will talk about. because this is much more, it's not really Geant4, okay? Whether we are using event-by-event description, whether we are using a condensed history technique, or we are using something that in between, okay? Some mixed simulation. How we describe ionization and Bremsstrahlung in high-energy physics with the secondary production threshold that I will talk about, Makoto already mentioned, the production cut. It's exactly the point with ionization and Bremsstrahlung that the low-energy secondary photon and electron emission we don't describe individually, but the higher than a given threshold we describe individually. Now with the Coulomb scattering, it would correspond to something that when there is a high-angle scattering that makes important change in the direction, that we describe individually, but the low-angle part, that's just small deflections, we can describe very well with the multiple scattering theory. So if we combine these two parts, and if you want, here we have not secondary production threshold, but angular deflection threshold, to describe something in a condensed or an event-by-event basis. These are called mixed simulation models, and we have models like this. The problem is that after, if you go down with energy, that everything will fall into single scattering, high-angle scattering part. And some multiple scattering models, we have multiple scattering models that describes as accurate the whole story as single scattering. So it's again, we have several models to describe it. You can go for a fast but less accurate things, or I can tell you which is the model, but you can find out if you go to the EM standard option 4 physics list, you see what we are using there. Because as I told you, in the electromagnetic, in the EM option 4, constructor is the best description that we can do today. So what we say is that if you are unsure, you make a short run with option 4, the electromagnetic part. Then you see what you should get. But I will talk about it later.
So now we should have the hands-on sessions. So first of all, we'll have another coffee break here. And then we should go all together so that you can find for the first time, most of you don't know what it is, the hands-on room. And then we all go together in 10-15 minutes after we start the coffee break. Then we move there. We should be there by 3:20 or 20 past 3 or 3:30 or something like that. Okay, so go to the coffee break, and then in the sequence we go to the hands-on. Yes, tomorrow morning, again here at 9. Okay?